Okay, welcome class. So we are starting chapter 2 of Journal 3, which is about derivatives. So this will be an exciting time. We'll be able to get into understanding that there's several ways to compute derivatives in R3 and higher. Okay, so we're going to start off with the first maybe about 8 or 10 pages here in this video. And the first function I want to talk about is z is a function of x and y, and it has this explicit equation, x cubed plus 2y squared x. Okay, and so again, back when life was simpler, we had y was a function of x, and maybe it was given by x cubed plus 2x. And so it was simple over here when we said take the derivative. There was only one variable to take the derivative of, and so we would say f prime of x, and we have all these different rules. These are just some nice power rules and a linear rule. We're going to use those same rules, but things are going to get extended because we now have higher dimensional space. So here when we say take a derivative, we have to be explicit. We have to say with respect to what? We got two variables. And so there's many ways to do this. And the first type of derivative we're going to do is what's called a partial derivative. So we want to take the partial derivatives of this function. Now there's a partial for every variable you have. So there's going to be a partial in this case with respect to x and with respect to y. And there's several notations for this. So we could say f sub x, xy. So it's kind of like our prime. And we'll have a partial with respect to y. So of your two independent variables, you have a partial with respect to them. If we had a R5 function, we've looked at some of those, and you'll see some in this chapter. If we had an R5 function, that means there would be 4 independent variables. And so we'd have a partial with respect to each of those, so we'd have 4 partials. Okay, so in this case, how do we compute this partial? Well, the key here is when we see a partial with respect to x, is that that's the variable we're going to focus on, and that means anything else is a constant. So we're going to treat this y like a constant. And so what often, I do this in the beginning and it often helps students, is to think about the original function. When we'll come back to the with respect to y, let's just focus on with respect to x now. So when x looks at this function, x, I'm going to kind of boldface this here, x is the variable. And so this 2y squared is just a constant. It's a little bit more complicated looking constant than just 2 or 7, but treat it just like that. Okay, so now when I take the derivative with respect to x, I'm going to say x cubed. What's the derivative of that with respect to x? Well, that's no problem. That's just like we did over here in R2, times the power down a power rule. Okay, now over here, 2y squared x. What's the derivative of that with respect to x? Well, it's just this big constant times x, which is just like what you did over here. This is the linear rule. So we're going to take the derivative and just get 2y squared. That's our partial with respect to x, but we also have to go back and compute it now with respect to y. And we'll eventually come back and tell you what these mean, but for now, the first part of this chapter, we're going to practice like cranking away with computations like we are the human calculator. So we're going to get good at those, and then we'll come back and explain multiple ways of thinking about what this actually means. We'll understand it geometric, we'll understand it visually, we'll understand it in terms of a business marginal effect. So many ways of understanding a derivative. Okay, maybe before we do that, let's evaluate f sub x at a particular point. Let's pick one that's kind of easy to plug in. Let's say 1, 0. Just like you did before, you could evaluate a derivative at any point you wanted. So this would be 3 times 1 squared is 3 times 1. So 5. And back here, we remembered what that meant. that was at when x was 1, and we were on our graph, the slope there was 5, which meant for a 1 unit increase in x from 1 to 2, y increased about 5 units. Right, so that was the interpretation back in R2. And as opposed to what we're going to say over here in R3. But it's just function evaluation, but you're evaluating the derivative. So we do the same thing here. F sub x at 1, 0 just says plug in 1 for x, 0 for y. And so we'll get 3 times 1 squared plus 2 times 0 squared, which is 3. Right. And we will have a similar interpretation that we had over here. We'll come back to that for a moment. For now, we just want to make sure we can compute the partial and evaluate it. Okay, that was all with respect to x, but now we have to come back and do this with respect to y. So I'm going to make a little space here actually and rewrite the function from y's point of view. So f is a function of x and y, and it's x cubed plus 2xy squared. Now y is the variable I want to take the partial with respect to. So I'm just going to boldface that, sort of highlight it, just to remind me that that is the variable. Everything else is a constant. And so I've just moved all the constants in front. I could have left the x over there, but I've just moved them all the constants out in front. And so now I'm going to look at this, and I like to tell students it's like putting on special goggles that make the y jump out, the variable that you're trying to differentiate with respect to. So I put on my special goggles, and now boom, y jumps out, and I want to take the derivative of this with respect to y. Well, the first term, when y looks at it, that's just a constant. There's no y's in there. It's just like 7. What's the derivative of 7? 0. Okay, so we get a 0 here, plus just by the sum and difference rule, same rules we had over here. What is the derivative of this term with respect to y? So I have a constant 2x. So I'm really just saying what's the derivative of y squared, then I'll multiply that times this constant. Derivative of y squared is 2y times the constant 2x gives me 4xy. Another way of thinking about it, once you've done several of these, you get to practice in the first couple of pages of this chapter with some functions, just times the power, so 4x down to power y. Okay, so partial then of y at that same point that we're interested in. Again, that's 1, 0 is a point on this surface. So we have some surface, some three-dimensional surface, and we're at some point, and we're going to compute this partial. What is that going to mean? We'll get there. But for now, let's go ahead and do the calculation. So we're just going to plug in 1 for x, 0 for y into our partial. So we'll have 4 times 1 times 0 is 0. Okay, let's do one more partial derivative, and then you have several in this chapter that are worked out, and you'll add some more that you'll work on your own. And there's answers throughout. All right, so I'll put one down here. That was our first example. Let's do the next example where we want to look at this function. F of xy, so again, an R3 function with 2 independent variables, y e to the x minus x e to the y. Same instructions, take the partials. There are 2 partials, so we'll have f sub x that we want to get. So again, putting on your goggles with respect to x. So x jumps out, that's the variable. Everything else is a constant. So even though this looks pretty messy, this is just like 7 e to the x, right? So what's the derivative of e to the x? E to the x times the constant y. So y e to the x. Minus, by the sum and difference rule for differentiation, minus this second term. What is the derivative of the second term with respect to x? Looks pretty complicated, but again, this is just a constant, so you can imagine it being out in front. If we like, we can go ahead and write it that way. E to the y, x the variable, We like to think of constants out in front. So when you take the derivative of this term with respect to x, it's just like 7x. The derivative of 7x is 7, but we have something a little more complicated than 7. So that's just going to be e to the y. And again, you could evaluate that at some point, just plugging in the values that are given. Okay, partial with respect to y. Come back here, remind ourselves that y is the variable this time. Put on your y goggles. Boldface that one. Okay, so when I take my partial with respect to y, it's just carrying along this constant, so I'm just going to get e to the x minus x e to the y. Cool. All right, so that's our first skill that we need in this chapter, taking partial derivatives of functions.